Okay, let's dive right into this explainer on Play-First Programming. Today, we're going to build a complete, interactive physics sandbox entirely from scratch. You know, if you've ever felt completely bogged down by dry, repetitive coding tutorials, well, this is exactly the antidote you've been looking for. We're going to look at a fundamentally different way to understand software, not by just passively watching it, but by pushing it, breaking it, and seeing exactly how it reacts.
To start us off, I want to pose a pretty fascinating premise. What if you could totally bypass the dry textbooks and learn complex coding concepts simply through, well, joyful destruction? The core philosophy here is that true software reacts hard when you push it. So instead of memorizing syntax like a robot, you can absorb the genuine mechanics of programming just by playing around and intentionally causing a little chaos.
Our vision for this is to merge kinetic art with real physics. We're talking glowing neon marbles, perfect collision math, and beautiful light trails. Or conjuring up 5 solid spheres that react dynamically and leave these lingering overlaps of light across a dark canvas. Think of it like a digital physical playroom. Every time one of these neon marbles hits a wall, it bounces back using perfect math. And actually, rather than erasing the screen every single frame, we're going to use a really clever rendering hack to paint gorgeous trails that fade slowly over time.
All right, moving on to Section 1, Building a Digital Playroom.
So instead of writing out all that boring boilerplate code, we're going to use an AI, think Claude or ChatGPT, as our collaborator to build the initial blueprint. We feed it a very exact prompt. We ask for a dark gray canvas centered on an off-white background, a JavaScript array that spawns 5 large spheres moving in random directions, and the boundary logic to invert their speed the second they hit the canvas walls. Finally, we ask the AI to hack the animation frame. We tell it to paint a semi-transparent black layer over the canvas instead of erasing it, which gives us those amazing glowing trails. And, pro tip, we make sure to ask the AI to leave brief comments showing exactly where the sphere size, speed, and trail fade rate are configured. And this setup is just incredibly empowering. It's literally 4 brisk steps. Step 1, copy the code from the AI. Step 2, paste it into a blank text editor like Notepad. Step 3, save it as bouncers.html and make sure you select all files so it doesn't accidentally save as a text document. And step 4, simply double-click it to run. Boom! Suddenly you have a living physics engine right in your browser, with 5 bright spheres hurtling around, crashing into walls. Before you even touch anything, it's worth just watching it for a moment to really feel the rhythm of the bounces.
Okay, Section 2, Twisting the Physics Knobs. Now comes the fun part. It's time to take control and intentionally break the physics. We'll put the browser on one side of our screen and our code on the other. Our very first knob is the ghost trails. Look for the exact line in the drawing function where the canvas fill color is set. You'll see an RGBA color code, and at the absolute end of it is the number 0.1. That 0.1 is crucial. It tells the browser to paint a 10% opaque dark blanket over the screen every single frame. That's what creates the fading trail.
But watch what happens when we mess with that single decimal. If you change 0.1 to 0.005, the trails almost completely stop fading. Your marbles suddenly become infinite calligraphy brushes, weaving permanent neon lines all over the canvas. But if you push it up to 1.0, the trails vanish instantly. It leaves clean spheres with 0 history. It is a wildly powerful visual shift from just a couple of keystrokes.
Let's grab our second knob and inflate the marbles. We're going to crank the radius variable entirely out of proportion. In the setup section of the code, you'll find a line dictating the size of the sphere, which is probably something pretty small. We're going to crank that up so the math reads math.random times 100 plus 80.
The contrast here is just extreme. By altering that one single line of math, tiny, elegant marbles transform into massive, lumbering beach balls. You save the file, hit refresh, and these giant shapes instantly crowd the canvas. They smash into each other and the boundaries, filling the whole box with absolute chaos. You can literally see the boundaries of the digital box struggling to contain them.
All right, for our third tweak, we're going to defy gravity and inject pure kinetic energy. You need to locate the bounce calculation. That's the exact statement that flips the velocity when a sphere hits a wall. Normally, it just says -ball.dx to reverse the horizontal direction, but we're going to supercharge it by adding a 1.4 multiplier to both the horizontal and vertical reverse direction calculations.
Talk about a game changer. This completely transforms the behavior from lazy, slow reversals into violently ricocheting abstract lightning bolts.
Because every time a marble hits a wall, it doesn't just reverse direction, it gains 40% more speed. Within 5 seconds, they go from a leisurely float to ricocheting so violently that they literally blur into abstract lightning tearing up the sandbox. The energy just compounds and compounds. It's wild.
And that brings us to Section 3, the hidden coding lessons.
So here is the real secret of this whole explainer. This chaotic playground actually acted as a Trojan horse. Without seeing a single dry textbook, you just learned the mathematical foundation that powers every game collision system ever built. You saw firsthand how software determines boundaries by testing if a shape's center coordinate plus its radius exceeds the pixel width of the canvas frame. That single if statement you tweaked? That is the absolute bedrock of collision detection math.
You also organically grasped velocity vector inversion. Sounds like a fancy academic term, right? But you lived it. You experienced firsthand how multiplying a speed value by a negative number reverses direction instantly. And by adding that 1.4 multiplier, you saw exactly how to inject raw energy into a system. You basically proved to yourself how 2 tiny code changes dictate completely different physical behaviors.
And finally, you mastered alpha transparency accumulation. By controlling just a single opacity number on a background overlay, you created stunning motion blur and light trails. I think this proves that breathtaking visual effects don't always require hundreds of lines of complex code. Sometimes tweaking a single decimal place is all it takes to shift from a clean animation to beautiful, lingering kinetic art.
It really all boils down to this fantastic insight from our source material. Every game you've ever played with bouncing physics, from Breakout to Angry Birds, is built on exactly these 3 ideas. You just built the engine from scratch. I mean, think about that. That is the magic of this approach. You didn't just read about these mechanics, you manipulated their foundational architecture with your own hands.
So now that you've experienced the sheer power of learning through chaotic play, I have to ask, what complex system will you tear apart next to discover how it really works? When you stop treating code like a fragile museum piece and start treating it like a sandbox, there's absolutely no limit to what you can understand. So get out there, break things, and see what you can build from the pieces. Thanks so much for joining me on this explainer, and keep experimenting.